In our previous videos, we explored the distribution of sample means as a way to help us decide between two competing explanations for the result of an experiment. To go back, we talked about a situation where we were taking a single sample from a population we knew a lot about, the IQ distribution, applied a treatment, and got a sample of 16 individuals with a sample mean. Our sample mean was 106, which is different than the population we started with. However, we can't just jump to assuming that our treatment caused an effect, because that first explanation, the first explanation in all science, is one we have to reckon with. The explanation that there really is no effect of our treatment, and all we've measured is sampling error. So in order to understand the likelihood of sampling error, specifically the likelihood of 6 points of sampling error, we discussed the sampling distribution of the mean. Now, we actually saw a sampling distribution that would allow us to say something specific about the likelihood that this first explanation could account for this difference. Said differently, that if the first explanation is true, what likelihood would there be that we would get a 6-point difference in our sample means? To go forward, we looked at that situation where we took a random sample of size 16 from a population centered at 100 with a standard deviation of 15. Knowing what we do now about sampling distributions, we can say a lot about the likely sample means that we would get taking a sample of size 16 from such a population. In fact, this sampling distribution is really just a normal distribution, and we know a lot about the probabilities or proportions of a normal distribution. So, using what we know, imagine we were to z-score this sampling distribution. So, we take every individual sample mean, subtracted from the population mean, in this case the population mean of the sampling distribution of the means, divided by a standard deviation, in this case the standard error, or the standard deviation of the sampling distribution of sample means. If we do this, we'll be left with a unit normal distribution, that is, a normal distribution centered at 0 with a standard deviation of 1. Remember, z-scoring a distribution will always give us a resulting distribution with a mean of 0 and a standard deviation of 1. If the distribution that we're z-scoring or standardizing started off as normal, the distribution we'll end up with is unit normal. So, this transformation, this z-score for a sample mean, would allow us to take any sampling distribution, one that starts off normal, and convert it to the unit normal distribution. All I've done here is added some subscripts to make it more clear what we're doing. Notice that this is still the same z-score formula, except now we're working with sample means rather than raw scores. After doing this, we can return a unit normal distribution, but you might notice that we can ignore completely the fact that we had to do the sampling experiment. If we just started off with our context, that is, a population that's normal, that we took a sample of size 16 from, all we need to do in order to locate our sample mean in a sampling distribution of the means is know the characteristics of the sampling distribution. And since we know a lot about sampling distributions, we'll know that z-scoring any sampling distribution that starts off from a normal population will return the unit normal distribution. In fact, if we take a non-normal population and take samples large enough, then z-scoring that sampling distribution will also return the unit normal distribution. So, without ever doing a sampling experiment, we can apply that z-score for a sample mean to our sample mean and locate it in the unit normal, that is, the standardized sampling distribution of means. All we need to know is the standard error, that is, the standard deviation of the sampling distribution of means, and we can calculate where our sample is, that is, in a standardized way, where our sample is in the sampling distribution. And let's remember why we're doing this. That first explanation, the first explanation in science, states that all we're measuring is sampling error. Well, using this, we can say how likely it would be for us to obtain a mean of 106, or even one greater, if it really is the case that only sampling error is acting. So let's apply this calculation and see what insights we can gain. I'll take our sample mean, 106, minus the mean of the sampling distribution of sample means in this case, which is going to be 100. Remember, the sampling distribution of sample means always has the population mean. And to find out how far in standardized units our 6-point difference is, we'll divide that by the standard deviation of the sampling distribution of sample means. In this case, 15, the population standard deviation, divided by the square root of the sample size. If we do this, we'll get a z-score for our sample mean that's equal to 1.6. And remember, because our population started off normal, when we make a sampling distribution from that population, really of any sample size, we know the resulting sampling distribution will be normal. So, what we can compare this 1.6 to is simply the unit normal distribution, the z-distribution. So what we're doing is finding where that 1.6 value is in a standard unit normal distribution. And since we know a lot about the proportions of this distribution, we'll be able to say something about the likelihood of simply by sampling error alone getting a sample mean where we obtained it, a sample mean of 106. Although we started this conversation with the idea of forming a sampling distribution of the mean, remember, in practice, we never calculate the sampling distribution of the mean. Instead, we circumvent that process by knowing the properties of the sampling distribution of sample means, which allows us to simply z-score our sample mean in order to locate it in a unit normal distribution. The reason that works is because when we z-score any normal distribution, we end up with a distribution with a mean of 0 and a standard deviation of 1. So, if we know the sampling distribution, once z-scored will have that property, then we can simply z-score our sample mean in order to locate it in a sampling distribution. Remember, standardizing or z-scoring a distribution doesn't make it normal. That is, we have to have started with a normal distribution in order to end up with that unit normal distribution once z-scored. That's where the magic of the central limit theorem comes in. With sample sizes that are large enough, we can ignore the population distribution and trust that our sampling distribution of the mean will have that normal shape. Then, with a z-score transformation, we'll end up again with a unit normal distribution. In order to say something specific about that first explanation, that is, that sampling error alone was the explanation for our difference, what we're going to do is form something called a p-value, or a proportion more extreme value. Now, a p-value is simply a way of describing how extreme a score is in a distribution. So a p-value is the proportion of a distribution that's more extreme than a given score. For instance, what if I told you that only 2% of samples that could occur by chance were more extreme than 106? Well, that would probably convince us, at least a little bit, that it was unlikely that sampling error alone is what generated that value of 106. But what if I tell you that almost 90% of samples we're likely to get by chance alone are more extreme than 106? Well, in that case, you probably wouldn't be convinced that sampling error alone is a bad explanation. In fact, it's a pretty good explanation because most of the samples we could get have values even more extreme than the one that we got. So a p-value is simply a way of showing us how extreme our score is in a sampling distribution. Now, p-values come in two varieties. The first and probably most intuitive is what's called a one-tailed p-value, and that's the proportion of a distribution more extreme in one tail. By one tail, I mean in the same direction from the mean that we observed our sample. In our context, a one-tailed p-value would answer the question, what proportion of sample means have a value of 106 or more extreme, that is more positive, if chance alone was causing the difference, that is, in the sampling distribution of the mean we obtained. Now, another variety of p-values is called a two-tailed p-value, and that's the proportion of distributions more extreme in both tails. That's like asking what proportion of sample means simply by chance alone would be 106 or greater or 94 or less. This answers the question, how much of the sampling distribution showed sampling error as extreme or more extreme than what we have obtained. Now, a two-tailed p-value isn't always an obvious thing to do, but suppose we're flipping a coin 100 times simply to find out whether the coin is biased. Suppose we get 60 heads. Well, that's 10 more flips than we expected by chance. But if we got 40 heads, that would also be 10 fewer heads than we expected by chance. That's just as much sampling error, but it's not in the same direction. If we're trying to tell if the coin is biased, we may not care if it comes up heads more often or tails more often. We just want to know how much sampling error we obtained and whether that much sampling error is expected by chance. We'll see that two-tailed p-values have some better properties, but we'll come back to that in just a second. Let's look at our current situation. We obtained a mean of 106. This ended up with a z-score of 1.6. So, how much sampling error is that? Is that a reasonable amount to get simply by chance? Or is that an amount that we wouldn't expect to get very often by chance? To find out a specific answer, I'll launch the distribution and probability calculator that's in the teaching modules in JUMP. If you're using the journal that accompanies this module, you'll also find a link to this calculator. What I've entered here is 1.6 in the greater than value section. This returns a probability of 0.0548, which is telling us that there's 0.548 proportion of a normal distribution more extreme in the positive direction than a value of 1.6. So this tells us a little bit about whether it's reasonable to assume chance alone was acting. If we're simply taking samples from a population centered at 100, we would obtain a sample mean of 106 or greater about 5% of the time. Now let's try the two-tailed p-value. I'll click the outside value 1 and 2 and enter negative 1.6 for value 1 and positive 1.6 for value 2. Notice this addresses a slightly different question. How often would I get sampling error as much as I obtained, 6 points, if I was simply taking a sample from a population centered at 100 with a standard deviation of 15? In this case, we find that the probability of obtaining this much sampling error occurs about 10% of the time. So this may give us a slightly different impression about how unlikely our particular difference is due to chance. We'll talk about using both the one-tailed and two-tailed p-values, but notice that by knowing something about the sampling distribution of the mean and its properties, we're able to give context or at least some idea about the likelihood that that first explanation is reasonable. And remember, we're trying to discredit that first explanation. So notice that a p-value, when smaller, discredits that first explanation more. For instance, what if we found out that it was incredibly unlikely with just sampling error that we would obtain 6 points of difference? Suppose that two-tailed p-value was 0.001, a 1 in 1,000 occurrence if only sampling error was acting. Well, that would give us a different impression than this particular situation. So we need to be specific and we need to come up with a decision theory about how to utilize the probability information we have. But notice all of this is made possible by an understanding of what happens when we take samples from a population. That is, by understanding the sampling distribution of the mean. So let's back up and actually talk about the logic of hypothesis testing, which is in essence an application of this distribution of sample means.